Today I'm going to go through an overview of project assumption of physics that I gave at the University of Kansas this month, at the beginning of this month. So let me give you first a very quick high-level overview of the project. So the main goal of assumptions of physics is to identify a handful of physical starting points from which the basic laws can be rigorously derived. So for example, we want to be able to say that if we assume infinitesimal reducibility, we can recover the notion of a classical state. What does infinitesimal reducibility mean? Well, we imagine that we have a ball, we can throw the ball and study the motion of the ball, or we can take a red marker and make a red dot on the ball and study the motion of the red dot. So the system is reducible in the sense that you can study the whole ball, or you can study all the possible red dots that you could put on the ball. If you study one, you know the other thing. And it's infinitesimally reducible because you can make these red dots as small as you want, arbitrarily small. So under this assumption, the idea is that we want to be able to say that that's how we recover classical mechanics. That's what a classical system is. One that can be thought as made of infinitesimally tiny part that we can all study independently. On the other side, we want to be able to say that if we assume irreducibility, we get to the quantum state. So we have an electron and we can study the electron, but we can take a red marker and make a red dot on the electron and saying, oh, this red dot went here and so on. And it's because we can't interact with just a part of the electron. Either we interact with the whole electron or none of the electrons. So we only can get information, we can only access information about the whole electron, we can't access information about the part. And this is what it means that the system is irreducible. We can study the whole, but we can't think of the whole as made of infinitesimally parts and that we can study independently. So these are the things that we'd like to say, and we'd like to say so precisely that we can recover the math. And the problem is that if we really want to do it properly, we need to recover basic mathematical structures such as real numbers, topology, sigma algebra, and all that. So we need to do that at a high, at a low level, and we want to be able to say things like this. Science is evidence-based. Therefore, a scientific theory must be characterized by experimentally verifiable statements that are associated with a test. And we want to show that under this condition, we get the topologies and sigma algebras that we actually need for physical theories, right? So that we can recover the math from physical ideas. So this is a very high-level description of what the project is about. And you can see already that it's a very different approach to what typically people have in the foundation of physics. The standard view in the foundations of physics is that all the theory that we have right now are approximation of the one true theory. And the goal of physics is to find this one true law of the universe that is going to tell us everything. It's going to tell us how to unify general relativity and quantum mechanics and quantum field theories. It's going to tell us what really happens, or maybe we're going to have some ontology for the observable. We're going to solve the measurement problems and so on, right? And a lot of the people that work in the foundation of physics, they think that this is the real physics, and you know, what people are doing in condensed matter, that's just, you know, details that are interesting because the real thing is these fundamental laws, and that's it. And again, our perspective is very different from that, and it is for a reason, because the results that we got pointed all in a different direction. So one of the things that we found, for example, we saw before, is that requiring experimental verifiability already gives us these basic mathematical structures. We're going to see also later that the geometric structure that we have are actually equivalent to entropic structures. So you can fix the geometry or fix the entropy, and you can correlate one through the other. We can show that Hamiltonian evolution is equivalent to assuming deterministic and reversible evolution, isolation, and independence of the degrees of freedom. And if we add the kinematic equivalence assumption, the fact that you can reconstruct the momentum from the velocity, that you can reconstruct the state and the dynamics through the trajectories, then you recover the fact that you have massive particles and potential forces. So what these results are telling us is that the physical requirements and the assumptions are what is driving most of theoretical apparatus. So a lot of the things that we are taking are not really description of how the universe is, but assumptions about the universe or requirements that we need to have to be able to make a connection to experimental data. And so, for us, the saying that the goal of physics is to find the true laws of the universe is not a very productive point, because that's not how we are finding the laws of physics. The way we're defining is by layering out these assumptions and requirements. And so, for us, the goal of physics is to find models that can be experimentally tested, which also means that it gives more credit to all the other people that are not doing the foundation and they're looking at other models. And for us, it's a much more productive point of view. And so the view that we have in our back and our head is that the foundations of physics basically mean to find the theory of physical models, not to find the one true model that rules them all, but is to find a meta theory for all the possible physical models. So we want to be able to have general physical principles and requirements that we basically need to say these are going to be valid for all scientific theories, because otherwise we don't have connection to experiment, we can't get data and so on. And the idea is that from these very few physical requirements we get a general mathematical framework that every theory has to respect. And then within this framework, we can find specific assumptions, like we saw before, infinitesimal reducibility or irreducibility, to recover the other theories. And the other theories are now specialization of the more general theory. So everything that gets proven at the more general level is inherited to these other theories. So it's not that these theories are approximation to each other. No, they're just different instances of the same mathematical objects with more structure. If you come from the computer science, this is the superclass, and these are the instantiation of the superclass with more structure, right? So this is exactly what we want to do. And this also brings the foundations of physics closer to what the foundations of mathematics and computer science are, because in the foundations of mathematics nobody is looking for the theorem of everything, the theorem that proves all the other theorem. No, doing foundations of mathematics means doing logic, doing model theory, like studying essentially what mathematical theories are, what is mean to do mathematics, and study the limits and the structure that you have when you're doing mathematics. And same thing for foundations of computer science. Foundations of computer science does not mean that you're looking for the algorithm of everything, the algorithm that is able to replicate all other algorithms, but it's again trying to define what is a computation, what is a general model for computation, like a Turing machine, and what are the things, characterize the things that can be done and cannot be done. You talk about Oracle and all this. And so we want essentially to have a foundation of physics that looks very much like those, and in fact we're able to sort of inherit, not results unfortunately, but at least ideas and techniques from what those other people are doing. And so the two techniques that we have developed to be able to get more inside physical theories and to find these assumptions and this more general theory is reverse physics and physical mathematics. Now, reverse physics starts with the idea that we are going to take physical theories that right now I just described mathematically, and we are going to recover the smallest set of assumptions to derive the theory. So we want assumptions that are necessary because they are implied by the physical theory, but they're also sufficient because if we only take those assumptions, you're able to recover the full physical theory. And if you have a set of assumptions or starting points that are necessary and sufficient, it means that those assumptions are equivalent to the theory. So now you can either take the theory to be true or take the assumptions to be true, and you can do one or the other. And this allows us to sort of think about the structure of physical theory in a way that it's more intuitive, in a way that it's closer to physical idea than just mathematical instruments. It's called reverse physics, first of all because it's kind of a reverse engineering, but also because there is a technique and there is a community called reverse mathematics that basically takes theorems and again trying to find necessary and sufficient starting point from which the theorem can be derived. And again, you're going to have that if you do it correctly, then the starting points are equivalent to the theorem. So you can either take the starting point to be true or the theorem to be true, and it's the same thing. And by basically studying all these equivalences, you get a sense of what are the subsystems of mathematics. And this is what we want to do in physics as well. By studying all these different ways of re-expressing conditions that are equivalent to each other, then we can find these subsystems in physical theory and have a much more clearer understanding of what physical theories are. And then the other thing that we need to do is that we would like to do this all rigorously, so that we know that we have exhausted all assumptions that we need to recover real numbers and all the lower level differentiation and all the lower level mathematical structure that we have, so that we know, yes, with all these things that we are assuming, we actually can get all the mathematical structure, and then we know what all the mathematical objects represent. And so the idea is to start with physical ideas, physical models, physical requirements, so that we have semantics that it's clear, so we don't need an interpretation because we already know what is it that we're modeling. And from those physical ideas, physical model, we get some physical requirements for the formal system. And we translate those requirements into formal requirements in the math, so that we can generate the math that we need. And now the math is not just something that a mathematician cooked up that may or may not have physical significance. No, it's mathematics that is designed to represent physical theories, and we know what are the conditions in which that mathematical framework is valid. And we have a very good map between mathematical objects and physical objects, such that we can read any proof as if it were a physical argument. And this sort of changes completely the way that you see math and physics and their relationship, and we can do this in a much better way than I actually originally expected. So in this the rest of our presentation, I want to give you a sense of what both reverse physics and physical mathematics are. And let's start with reverse physics. And the best way to give you a sense is just to show you some result and see how it works. So here we have Hamilton's equation, and this is just Hamilton's equation rewritten in a slightly different way. So this S upper B is basically all the derivative of position and momentum in time. So basically what we call the displacement field. It tells you how the states are moving in time. This omega essentially switches the Q's and the P's and puts a minus sign in one of them. And this is just the gradient of the Hamiltonian. So we basically, instead of having these switched out with a minus, we're switching these two up with a minus, and then you just have the gradients. And you can also think of this as a rotation by 90 degrees. And this lower a is basically this contracted with this, in the same way that you have covariant and contravariant component in metric spaces in Riemannian with a Riemannian metric. Here we do something similar, but it's sort of the meaning is a little bit different. This just means it's rotated 90 degrees. And so you can take these two are equivalent conditions, and so the question is, what are the minimum set of assumptions that we have to make to get this set of equations? So it turns out that you need two assumptions. The first is deterministic and reversible evolution. The system undergoes deterministic and reversible evolution. Specifying the state of the system at a particular time is equivalent to specify the state at a future or past time. And there are multiple ways that we can implement this assumption. We could say that the displacement field is divergenceless, is incompressible, as many states come in a region, as many states flow out of the region. And so the divergence of the displacement field is 0. Or you could say the Jacobian of the evolution is 1. Or you could say that the densities are conserved through the evolution, meaning that you map the density in time, but the same value of the density is mapped to the same value of the density. Or that volumes are conserved through the evolution. And these are mathematical conditions. What do they mean physically? We can tell because statistical mechanics tells us that the volumes in phase space count the number of states. So if we have a transformation that maps volumes of with the same volume, regions with the same volume, we are mapping the same number of states to the same number of states. Then we are mapping states one to one. Therefore, the evolution is deterministic and reversible. Or since the volume is preserved, the logarithm of the volume is preserved, therefore the thermodynamic entropy is preserved, therefore the evolution is thermodynamically reversible. That's another condition. Or you can also say that the evolution conserves information entropy, or you can say that the evolution conserves the uncertainty of peak distribution. So any of these 8 conditions is equivalent to assuming deterministic reversibility. So you can pick one, and if you pick one, you have determined what assumption you have. And this is kind of like what again I would like to stress is that the same condition is implemented in different ways, and this is exactly what I was saying before, that we want to be able to express the conditions in different ways to get sort of a more of a sense of what are the macro systems in a physical theory. The other assumption that we need is that of the independent degrees of freedom. That is, the system is decomposable into independent degrees of freedom, that the variables that describe the states can be divided into groups that have independent definition, units, and count of states. And if we have this, again, we can implement it in 4 different ways. Now we can take any condition here with any condition here, and we're going to be able to show that it's equivalent to get one of the heuristic condition here. So the evolution leaves omega AB the symplectic form invariant, or the evolution leaves the Poisson bracket invariant, or the rotated displacement field, this S lower a lower b, is curl-free. The curl is 0, and if the curl of SA is 0, then there is it's the gradient of a scalar potential, and this is exactly what the Hamilton's equations are saying. So again, instead of just having this formulation of Hamilton's equation that tells us nothing, now we have a formulation in terms of assumptions, and we can take one here and one implementation here. So we have a 4 times 8 possible combination of ways to understand these equations that, of course, are going to give you a lot more intuition. And one of the ways that we can do is, for example, going and look at the principal stationary action with this idea in our mind and understand better what the Lagrangian is, what the action is, and why paths make the action stationary, make it minimized. So the correct space to look at this thing is the extended phase space, where we have position and momentum phase space that is extended by the time variable. And so now you can imagine that there is a flow of states that goes in time, right? So we have this flow that this S that tells us where the states are going, not just in position momentum, but in time. We are evolution in time. And again, if we have deterministic reversible evolution, if we take a closed region, as many states come in, as many states can come out, no state is lost or created as time evolves, which means the divergence of S is 0. And if the divergence of S is 0, it emits a vector potential. So S is minus the curl of a vector potential theta, and this minus is just put there to match convention. And what you can show that without loss of generality, you can choose a gauge for theta that is p, 0, and minus h, where minus h is the only arbitrary function. And if you now calculate this curl, recall that this is going to be the q dt, dp dt, dt dt, like this is the displacement field, tells you where things are going. You are actually going to recover Hamilton's equation. So this is a very direct way to see that Hamilton's equations are just assuming that your motion is incompressible and therefore you have a potential, and h is the time component of that vector potential. Note that this is also very similar to what we have when we do special relativity, the form momentum. It's related to this. Okay, so now we have a vector potential theta. What can we do with it? Well, we can take a line integral. We can take a gamma, right? It's going to be this curve here. And we're going to take the line integral of theta along gamma. The components of theta are p0 minus h. And the component of d gamma are going to be dq dt, dp dt, dt dt along the curve gamma. And so we have p times v plus 0 minus h dt over dt, which is 1. So this is pv minus h. That's the Lagrangian. Like the only thing that one needs to do is need to be able to write p as a function of position and velocity, because the Lagrangian has to be expressed in terms of velocity. And this is where we need this extra assumption of kinematic equivalence. We must be able to reconstruct the momentum from the velocity. It's an additional assumption. But the point is that This basically tells us that the action is the line integral of the vector potential of the flow of states, and therefore it's an unphysical quantity. Not only it's unphysical, but there is a gauge here. So we could change theta, we can change gauge for theta. It would change the Lagrangian, it would change the action, but we are not changing S. S wouldn't change. And this is, if you study Lagrangian mechanics, somebody might have told you that the Lagrangians are not unique for the system. This is why they are not unique. There is a gauge hidden there, and I think one should be able to prove that all Lagrangian theory have to be gauge theory in some sense. And this is something that once we are able to expand all of this to field theory, is going to be something that we are looking for. But anyway, the point is that the action is, we know what the action is, it's an unphysical thing, but the variation of the action, the funny thing, is that it's physical. So if we take the variation of the action, we are taking a path gamma and a gamma prime, and so we're doing the line integral over gamma minus the line integral over gamma prime, but we could also take gamma prime on the other side, so we are basically take the line integral on gamma and then in the opposite direction on gamma prime. We're basically taking the line integral on the contour of sigma, where sigma is the surface that is between gamma and gamma prime. So the variation of the action is just the line integral of theta on the contour of sigma. And now we can just use Stokes' theorem. So now we have the line integral over, the surface integral over sigma of the curl of theta, but the curl of theta is minus S. So the variation of the action measures the flow of states through the surface sigma between the path and variation, and that is physical. Now, if you imagine that you have a trajectory, that your gamma is a trajectory, the flow is always tangent to gamma, therefore it's always going to be tangent through sigma. No flow is going to go through sigma, and therefore the variation of the action is going to be zero because the flow is zero. But if you take a path that is not an actual evolution of the system, then you can find a variation where you catch some flow, and then you're going to have that the action is not stationary. So I'm not expecting you to fully understand everything right now. I have other videos, you can go read the paper, but the point is that we can understand this stuff, right? We can, all of this is just properties of vector calculus and differential geometry, that there is nothing so complicated about it. Like the complicated things were actually to tease out these ideas from the math, and the assumption that we have, again, there are determinism and reversibility, there is kinematic equivalence, and there's going to be the independence of the degree of freedom when we go and work on the multiple degrees of freedom. So this is the point that with reverse physics we can really understand the current theory a lot better and get much better intuition. But the thing that I think is most exciting for me for reverse physics is the ability to sort of tie in not just a different perspective within a single theory, but tie in the same perspective across different theories, such that you can start understanding physics as a single thing instead of all these different pieces that are completely disconnected to each other. So to do that, let's start with a question that seems to be just a quantum mechanics question, but we're going to actually try to tie in classical mechanics as well. So we know that quantum mechanics has this thing called the uncertain principle, and we really think it as a property of quantum mechanics. And so now the question is it really just a property of quantum mechanics, or there is a classical correspondence to the uncertain principle as well? And while we do that, well, we saw before that Hamiltonian evolution was tied into some conservation of uncertainty. So we want to understand whether there is some relationship between this uncertainty and the uncertainty of the uncertainty principle. So yeah, suppose we have a distribution and we want to characterize the variance of that distribution. We can do that through the covariance matrix. So we're going to get the variance of position, the variance of momentum, and the covariance. And the determinant of this matrix, which we're going to call here sigma square, it's sort of a better way to characterize the variance between the two, because it takes into account correlations. And what happens if you have a really peaked distribution, like a distribution where the support is very small, essentially to a first approximation, the covariance matrix sort of characterizes the full distribution. And if you have a peak distribution, again, one of the things that happens is that the flow that is going to be moving this distribution around, when we're doing mechanics, is going to appear linear to the distribution because there's going to be small variation. And so the covariance matrix are going to transform linearly. It's basically going to be sandwiched in between two Jacobians. And so the determinant of the covariant matrix at a time t is the determinant of the Jacobian, the covariance at the initial time, and the determinant of the Jacobian. Now, if we are studying Hamiltonian mechanics, during Hamiltonian evolution, the Jacobian is actually equal to 1. And so you basically have the determinant of the covariance matrix is invariant. So at time t, the product of the variance minus the covariance square is equal to the initial uncertainty. And note that the covariance is always a positive thing. So all these, this is always going to be greater than this. So we have that throughout the evolution, sigma q, sigma p is going to be greater than the original sigma at time 0. And so the uncertainty is bounded during the classical evolution. Again, this looks very closely like an uncertainty principle and already tells us that this equation is going to have an equal only if you don't have a covariance, if these ellipses are standing straight or like that, right? And okay, but this is not exactly what the uncertainty principle is about. The uncertainty principle is about the uncertainty related to a constant, is not related to some initial condition of the state. So let's see if we can find something better. And let's look at information entropy. Information entropy also relates to the uncertainty. And so let's try to understand exactly how information entropy actually is related to uncertainty. So let's plot the entropy against the uncertainty. And for the entropy, we mean the information entropy, so minus the integral of rho log rho. And one of the things that we have to do here is to fix the unit. Whenever we're doing reverse physics, we always want everything to be physically meaningful, and this rho is the inverse of volume of phase space, and you can't take the logarithm of a quantity that has physical dimension. It has to be a dimensionless quantity, so we multiply by a constant h, but this h has a direct physical meaning. If you take rho as a uniform distribution over a volume h and you calculate, you're going to have that the entropy is 0. So we don't know that there is a Planck constant, we don't know anything, we just know that we're going to have a 0 for the entropy, and h is the thing that sets the 0 for the entropy. It basically tells us what is the spread for a distribution that has 0 entropy. Okay, so once we have that this is clear, we can now plot, and what we find is that if you fix the uncertainty, if you fix sigma q, sigma p, and you go up, what you're going to find is that the Gaussian maximizes the entropy for a given uncertainty. So you can go more at higher entropy than what the Gaussian allows you to. And this is the entropy for a Gaussian. It's a logarithm 2 pi e sigma q sigma p over h. And look at this. This looks like another uncertainty relationship. Sigma q sigma p is greater or equal to h over 2 pi e times the exponential of the entropy, and we have an h over 2 pi, we can call this h bar. And so we now have that sigma q and sigma p is greater or equal to h bar over e times the exponential of the entropy. And now this is something that is true at every moment in time, even if we don't have evolution. The idea is that the entropy is putting a lower bound on the uncertainty, and of course then Hamiltonian evolution conserves entropy, right? But even if we didn't have evolution, that relationship would still be true. Again, this is better because we don't have initial conditions. We have a property of the system, and the system has that property, right? It's a property of the system that the uncertainty cannot be bigger than what the entropy allows. But again, we would like this bound to be universal for all possible states. And note that if we had a lower bound on the entropy, then that would put a lower bound on the uncertainty as well. So the question is there anything in physics that puts a lower bound on the entropy? And the answer is yes. There is the third law of thermodynamics that has many different ways of of expressing itself, but one of the way is to say that the entropy is cannot be negative and it's zero only at zero temperature with a crystallized substance. Okay, so now let's include that in our reasoning. Again, we are mixing classical mechanics with ideas from thermodynamics, and what we're doing now is essentially excluding this region because we have the third law, nothing can have zero entropy and below, and nothing can go below zero entropy. And so now sigma q sigma p has to be greater or equal to h bar over e to the zero, because that's the lowest entropy that we can have, and therefore the to be zero becomes 1. And so sigma q sigma p is greater or equal to h bar over e, and I call this the classical uncertainty principle. And now we can compare two. We have the classical uncertainty principle, the quantum uncertainty principle. This blue line is the classical bound given by the Gaussian, and this is the quantum bound given by the Gaussian. And you can see that E, right, is, since it's a little bit bigger than 2, in the classical case we can squeeze a little bit more uncertainty, and we can do, remember, because we saw that we get the equal, right, when we have Gaussians that are completely uncorrelated and independent. So we can get to that h bar over e on the assumption that the distribution in position momentum are independent, which is exactly what you can't do in quantum mechanics because you do not have a joint distribution. So things make sense at a conceptual level. But one of the things that we should note is that the entropy of a quantum system is already non-negative because pure states have zero entropy, so you cannot really have states with zero entropy. So quantum mechanics really incorporates the third law. Instead, in classical mechanics, it's not incorporated. We have to tack it on separately, right? So quantum mechanics is better because it's putting this idea together at a more fundamental level, so you can't have these states that can't actually be, that don't actually exist. And another thing that you should see is that the Gaussian bound becomes similar very quickly. Just with a couple of units of h bar, we already have the Gaussian's bounds are already very similar. So the question is whether this is the only difference. And one way to ask that question is that if they are really the only difference between classical mechanics and quantum mechanics is what happens at lower entropy, then we should expect that at high entropy, quantum mechanics is very well approximated by classical mechanics, and therefore we should recover classical mechanics as a high entropy limit of quantum mechanics. And I had this conjecture for a number of years, not knowing exactly how to prove it. So what I did a year ago was to post on my channel where I do research, to post a video with that conjecture. And about a month later, an atomic experimental physicist wrote to me, and with some ideas, and we started collaborating, and we wrote a paper together. So this is why I believe that one of the problems also that we have in the foundation of physics, that we have all these people that are trying to think everything by themselves and create new things, and I really think that what we really need is to get insights from a lot of different areas and pull them together, and that's how we are going to get actually a better foundation of physics. That's why I try to collaborate more. That's why I have this YouTube channel, and you're here listening to this, because I really think that's how we make progress. And unfortunately, academia is not quite set up to be able to do this large-scale, multidisciplinary research. So this is why I'm trying to do it, and I'm here, and sometimes I do get good results, so, you know, let's do it. Okay, so how does this work? Well, in principle, it's not even that complicated. The idea is that we want to take a level set of entropy, so all the mixed states that have a given entropy, and increase the entropy in a way that the entropy is increased all in the same way. So that if we had a unitary map that maps this state to this state, then this is mapped here, this is mapped here, and so these states are also mapped by the transformed unitary map. And so it turns out that if we want to be able to do this, then if we start with the commutator with x and p and see how that commutator changes when we transform x and p, we need that the commutator essentially to be rescaled by a constant. If you have something more complicated, then you're going to have some region of phase space that are increased at an entropy that is different from another region of phase space, and therefore you're not you're not increasing the entropy homogeneously, and then you basically destroy the unitary group, and the deterministic and reversible group are not mapped one-to-one. Okay, so this is essentially what the limit means, and if you want to go, you can look at the paper, but there's another way to look at this. So instead of saying, okay, let's go up in entropy, let's stay where we are in entropy, but let's take the pure states and bring them down in entropy, right? So we take the zero of the entropy and we bring it down to minus infinity, right? It's kind of like the same thing. We're changing the relative instead of changing the absolute. And so instead of saying let's start with a space where the commutational relationship between x and p are IH bar, and let's end up with a space where there are lambda IH bar, let's redefine the original space such that the commutation between x and p is IH bar over lambda, such that when we do the transformation, we get back the IH bar. And if we're making this lambda that goes to infinity now, what happens is that it's h bar over lambda that goes to zero. It's this commutator that goes to zero. So it's kind of the same way to say, okay, let's take this h bar of this commutator and make that go to zero. Okay, of course, that physically doesn't make any sense because h bar is a constant, right? But mathematically, we're basically saying that lowering the entropy of the pure state to minus infinity, it's equivalent in a sort of sleight of hand kind of way of taking h bar goes to zero and then starting the group contraction and recovering the standard way the mathematicians recover classical mechanics through this mathematical technique. So what we have recovers that mathematical way of doing things in a very precise way, so that we have a physical meaning. So in the same way now that we have relativistic mechanics that you need at a high speed, but when you go at low speed, you can get non-relativistic mechanics. And mathematically, that's the same as taking the limit of c that goes to infinity, which again, physically is horrible. C is a physical constant, it doesn't change, but sort of mathematically saying that we are at low speed, it's kind of the same as saying we have a very large speed of light that seems to be at infinity. Well, in the same way that we're doing this, physically what we have that quantum mechanics is necessary at low entropy, but if we go to high entropy, then we can approximate it with classical mechanics, and making this high entropy limit in physically, it's kind of the same mathematically to say that h bar goes to zero, even though it's completely horrible because h bar is a constant and the constant shouldn't change. Mathematically, you can study that thing by doing the same exact thing. So you see, now the two types of limits that we have for non-relativistic mechanics and we have classical mechanics are of the same type, both sort of conceptually and mathematically. And in both cases, you see that there is no mechanism for this limit. So if you were studying the low speed limit for non-relativistic mechanics, you're not going to ask what is the mechanism that makes the speed slow, right? That doesn't work. Like, it's if you're studying a system for which the speeds are low, then you can approximate it with non-relativistic mechanics. There's no mechanism. Maybe there is a mechanism, some condition, but it's not that you need a mechanism. It's just if you happen to be in those conditions, however you are in those conditions, you can make that approximation. So the same thing for quantum mechanics. If you have states at high entropy that are suitably described at high entropy, you don't need the full quantum mechanics. You can get away with classical mechanics, and there is no mechanism required for being at high entropy. It could be that you have some entropy production that's coming in from the environment, the coherent, okay, those are mechanisms for which you could have high entropy, but you could even just be studying an electron, and the uncertainties in your trajectory of the electrons that you're putting in a particle accelerator, for example, are so big and everything is so large compared to the uncertainties that you have, that you might not need to use quantum mechanics to study the trajectory of an electron in a large magnetic field. You can get away just by saying, okay, I have a classical charged clump and I'm studying how that's going around, right? So it's really nice because this completely cuts away with a lot of problems that people in the foundations are trying to find classical mechanics through some kind of mechanism. And we basically say, we don't care about the mechanism. You can have whatever mechanism you want as long as the entropy is high. And if the entropy is high, then you can make the mathematical limit in that way, and that recovers classical mechanics, and that's the way that you do it. Now, the other way conceptually that this clarifies, it tells us what quantization is. So you have this direct correspondence principle where you take Poisson brackets and substitute them with commutators, and then you're quantizing. Well, what is it that you're doing? Well, now we know what you're doing. You're basically asking for a theory with a lower entropic bound that recovers classical mechanics at high entropy. That's what you're asking. This is what this thing is doing. So quantizing a classical theory, it's not some like weird thing. You're just putting a lower bound on the entropy. And the cool thing is that there is only one way to do it. The Moyal bracket is the unique one-parameter Lie algebraic deformation of the Poisson bracket. So if we are looking for some structure that has some Lie bracket, that has a parameter, and you take that parameter, and in that limit, in some limit, you're going to recover the Poisson bracket, you're going to recover classical mechanics, you need to have quantum mechanics. You have the Moyal bracket, that it's another way to express the commutators of quantum mechanics in phase space. So not only we are basically able to say, oh yes, classical mechanics is the high limit of quantum mechanics, but quantum mechanics is the theory that lowers the entropy of classical mechanics. Like it's the same thing. And so we see that entropy is really this fundamental role in this relationship. You may ask, but why? Why is it strange that entropy is such a fundamental role? And it's actually not a strange thing, because what happens is that all the geometric structure that we have in both classical mechanics and quantum mechanics are essentially there exactly to tell you what the entropy of statistical ensembles is. So in classical mechanics, we have that we have a symplectic manifold, again with the symplectic form that tells us volumes and area, and the volumes and area we saw before are count of states. So if we have a uniform probability over some region of phase space, then the probability density is just the inverse of that volume. And if you want to calculate the entropy, well, the entropy is just going to be the logarithm of that measure. But you see, the logarithm is an invertible function. So either you tell me the volume of all the regions, and then you can go and calculate the entropy of all the distribution, uniform distribution of all the volumes, or you could give me the entropy of all the uniform distribution of all the volumes and reconstruct all the volumes of the region, reconstruct the geometry. So all these three structures, the geometry, the probability, and the information theory, they are so interrelated that you can't specify one without specifying the other. Now the same applies in quantum mechanics as well, even though the mathematical structure that we have right now are completely different. So in quantum mechanics, the states are in a projective Hilbert space, the geometry is given by the inner product, and the inner product also gives you this probability of transition. And if you have a uniform distribution between two states, you take two pure states and you mix them with 50% each, then you can go and calculate the entropy of that mixture. And the entropy of this mixture is the Shannon entropy of the coefficient that depends on p, like 1 plus square root of p over 2 and 1 minus square root of p over 2. Now this is a horribly complicated function, but it's invertible. So in principle, you could say, I could give you the inner product or the probability of transition between any two states, or you can give me the entropy of all the uniform distribution among two states, and from the entropy I can recover that inner product, I can recover that probability, and everything works fine. So this kind of flips around the idea that we currently have, that statistical mechanics and thermodynamics are things that are built on top of mechanics. No, it doesn't work like that, because you cannot define mechanics without already defining all the things that you're going to need in statistical mechanics and thermodynamics and vice versa. So really the idea is that when you define these physical theory, you're defining them, both the mechanics and the statistical mechanics and thermodynamics, in one step. And so The mechanics is really the idealized case of statistical mechanics, where you can think about these ensembled as less spread out as possible, and you're studying a deterministic and reversible motion of those ensembles. So again, I hope that this sort of gives you an idea of how reverse physics tells us that there are not many independent concepts in a physical theory, right? There are all these pieces that we can translate from one to the other, and in the end of the day, there are not so many moving pieces. And extracting the principle as an assumption behind the laws and seeing how all these things are equivalent to each other gives us a solid intuition that cuts across fields and can give us new insight, new result, new ways to approaching different problems. And this is why I really think that this approach is a lot more productive than trying to figure out what is the latest theory of everything that then you can't test experimentally anyway. And again, this is all nice. We are able to understand things more thoroughly physically, but at the end of the day, we need to be able to be sure that all these principles that we're setting forth actually recovers everything. And to be able to recover everything, you need to recover all the math. And the only way to be sure is to start from scratch and recover the mathematics from physical idea, such that all the mathematical objects that we have a justification that tells us this is why we're using these mathematical objects in this case to represent these physical ideas. And this is the job, the goal of physical mathematics. But before talking about the physical mathematics, let's give you some example of unphysical mathematics. Mathematics that we use, it's not quite what we should have for physics. So, in differential geometry, tangent vectors are defined as derivation. Like a lot of the time when we introduce vectors in physics, we think of the old way of introducing vectors with infinitesimal displacement and all that, which maps very well to the physics. But if you open up a textbook in differential geometry, vectors are typically defined as maps from a smooth function to a number, which you can imagine that basically you have a vector v, and a vector v is essentially a directional derivative that takes a function and gives you the value of the derivative of that function along a particular direction. So for example, f might be the temperature field, and then this vector would tell you the derivative at a point of the temperature in a particular direction. And mathematicians do this because you can give a sort of an algebraic structure to the tangent space, which is convenient to do a lot of things in math and so on. But what's the problem? Well, the problem is that it doesn't really work well with units. So the bases here are the derivative of the function with respect to the coordinates. And the problem is that in physics, all the real numbers have to have units. There is never, either it's just a rescaling, right? But if there is a function, this function f is going to give you some unit, and this derivation is going to have to give you some units. So if you are taking the derivation with respect to the radius in polar coordinates, this would give you the original unit of the function divided by meters, and then if you're summing it with the derivative along the angle, that would give the original units divided by radians, and you can't sum these two things because the units are different. Now, if you're a geometric space, you can sort of fudge it and do something, but if you are in phase space where, you know, the q is in meters and the momentum is kilogram meters per second, you can't really resolve this problem. So this way of defining the tangent space, the vectors in terms of derivation, doesn't work that well. The old way of defining vectors in terms of infinitesimal displacement actually works a lot better, though it's kind of being disused. So it's a lot of the new results in differential geometry are in the new language. But this is an example to me where you have things that are mathematically precise, they're not really capturing and formalizing the physical object that we need. And again, the problem is that we don't really have just real numbers. We have real numbers with units, and so things have to work well with that. So that's an example. Another example is from quantum mechanics, where states are represented by square integrable function. And so this is a Gaussian wave packet. So it's a square root of e to minus x squared, and this is going to be a wave packet, and you can go, and this integrates to 1. It's normalized, so very good, it's a state. And the uncertainty, the variance of this distribution is 1/2, and I chose 1/2 because things are going to make mathematically are going to be cleaner with this example. Now, you can also take this other bell-shaped distribution where the tails are fatter, so you still have something that integrates to 1, but the variance actually does not converge. You get infinite variance, again because these tails are so fat that basically it makes it so that the integral does not converge. And so having something with an infinite uncertainty doesn't really is not really something that is an approximation on anything what we can do experimentally, because you can imagine, if we made an approximation of this, we would make a cut, right? But for the cut, the variance would be finite, and every cut will give you a finite variance. You're never going to converge in some meaningful way. You're always going to be infinitely far from where you should be to be able to actually have a good approximation. So this is not an approximation of something that it's reasonable. And again, the standard approach in physics would just be, well, we just disregard this. We only use this. The problem is that you can have a coordinate transformation, this coordinate transformation, that changes this into this. So meaning that an observer sees a Gaussian and another observer sees something different. And actually, one of the person that left me a comment told me that this is actually a technique called Gaussification that is actually used. So it's not even such a cooked up, made up example. It's something that actually people do. And so you are mapping these things from finite expectation to finite expectation, and potentially you're basically saying, well, look, one sees a finite thing and the other one says an infinite thing. But even worse, you can make a Hamiltonian, you can make time evolution such that you oscillate between this and this in finite time. Because all unitary evolutions are, in quantum mechanics, are just rotation. So you can take, whenever you have two vectors, you can always start rotating from one to the other, and that's just a unitary evolution. So you could have something that oscillates between finite expectation value to infinite expectation value in infinite time. And this is really a problem of the Hilbert space, because there is a theorem that tells us that every continuous linear operator defined on the whole Hilbert space is bounded. So position, momentum, energy, number of particles, all these operations cannot be defined on the whole Hilbert space. So in some cases you're going to have infinite or undefined expectation value, which again don't make much sense. It means that if we think of as the unitary groups as the group of coordinate transformation of time evolution, it's too big. It's moving things from physical to unphysical. We probably don't have the right group, which probably means we don't have the right symmetry, which probably means that some problem that we have with infinite dimensional space in field theory is related to all these things, and it needs to be solved at the most fundamental layer. We need to know what is it physically that we need to physically represent. So this is basically a sketch of what we have right now. We have the physical world, which is an informal system because it has to connect to experimental verification. We need to have experimental procedures, and experimental procedures are not formal things. There are things that have to do with reality, has to be touched, and so they're always going to be some kind of informal and somehow amorphous, not completely crisp. But then we have mathematical representation of these physical objects, and these are going to be nice and crisp, well-defined objects. And we would like to have maps that take a well-defined physical object to a well-defined mathematical object. We make some computation, and then we can go back. And of course, this map is many to one because many different objects can be idealized and formalized in the same way, but then we know in physics what we started from, we know how to get from. The problem is that sometimes we have calculations that give us some other objects, and some other objects is ill-defined physically. Or we have some other procedure that gives us mathematically defined objects because we haven't really cleaned up the physics well. Or we have real physical objects that are mapped to ill-defined. We have all of these things. And this is the current state of the art in theoretical physics. And somehow this is accepted. And I think this is a fundamental problem. And having a good foundation for physics means cleaning up this mess. Like, we are not gonna be able to clarify. I don't think we can go and proceed with, you know, your quantum gravity or all of this until we have cleaned up all these things. There might be problems that we don't even realize that we have. So this is what we like to have. We'd like to have things that map to a set. So we have a set of well-defined physical objects. We know what these things are, and that they map to a set of well-defined mathematical objects, and we can map one to one, and we always map back and forth, and we know how to map. And the thing is that the observation in physical, that is the core of physical mathematics, is that you can do this map well if and only if the physical specification, that is the boundary that you said how to define these physical defined objects, the thing that tells you these objects are in and are out, maps to the mathematical definition. Because if this physical specification does not map to the mathematical definition, that's exactly when you're going to map some physical objects outside of the mathematical definition. So the only way for this to work is if your definitions map well as well. Not just the object, but the definition that you put on one side map to the specification on the other side. And so we say the mathematical definition is physical if it captures and only captures an aspect of the physical system. And this is what we need to do. We need to understand how to do this mapping well. And so how do we do it? Because we don't have a standard of rigor to do this. And so we had in physical mathematics, in exceptional physics, we have to figure out a standard of rigor for how to do this. So that we don't just, oh yeah, we have the vibration of the whatever space. No, we need to understand how to do it. And so we have to start with axioms. And the axiom have to be some intuitive statement about the things that we want to describe physically. So for example, we have the axiom of mixtures that tells us the statistical mixture of two ensembles is an ensemble. And if you study statistical mechanics, and if you are a physicist or an engineer, this is obvious to you. It does not require any further description. Yes, of course, that's what we do. But if you go to a mathematician, he will tell you, this is not precise. What is an ensemble? What is a statistical mixture? And so you need a formal definition. We say formally an ensemble space E is equipped with an operation plus called mixing, noted with the infix notation PA plus P bar B. This P bar is just a shorthand notation for 1 minus P, with the following properties, and then there are a bunch of mathematical properties. And now the mathematician is going to be happy because we're using set theory and all these funny symbols, and says, okay, this is finally precise. But now we have this dichotomy. We have two things, right? We have an informal intuitive statement that is saying one thing, and then a formal requirement that is saying something completely different. And we need to reconcile these two. And how do we do that? With what we call a justification. And the justification has to show that the formal requirements follow the intuitive statements. And this justification will feel like something that in the 1800s would have considered a proof, but with the standard of rigor of mathematics nowadays is not considered a proof because they're elements of the informal system. But we need these things to guarantee us what is the reasoning, what is the realm of applicability of the formal requirement, and how exactly they descend from the formal intuitive statements, such that we are sure that we're making that map correctly. So for example, we're going to say this axiom captures the ability to create a mixture, merely selecting between the output of different processes. Let E1 and E2 be two ensembles that represent the output of two different processes P1 and P2. Let a selector says P be a process that outputs two symbols, the first with probability P and the second with probability 1 minus P. Then we can create another process P that, depending on the selector, outputs either the output of P1 or P2. So we're giving a precise model of what it is that we are describing, so that as physicists and engineers we can understand what this thing is. and then justify why this model satisfies these properties, such that the mathematician is guaranteed that the things that we're saying are actually good and we can guarantee them from the physics, right? So that we know what we're talking about and everything maps. And once we have that, the idea is that we can go back and read everything the mathematician wrote, and we can understand it because the model is clear from the get-go. There is no interpretation. We just have a physical model that is well specified. Okay, so let me give you an example again of how it works, because giving you an example is much better. So we start, for example, with principle. We want principles because principles are going to be requirements that we always have to satisfy to do something physical, right? So an assumption is going to be something that it's valid in some cases or not. We assume it to be true, even if it's not true for convenience. But a principle has to be something, no, this we must have, because otherwise it just does not make sense. And the principle of scientific objectivity tells us that science is universal, non-contradictory, and evidence-based. So science is about statements, things that are true or false for everybody, that are associated to experimental tests. Which means that some things that are not testable, things that are subjective, are not going to be the subject of study, of science, not because they don't exist, just because we can't make experimental tests. So the question of whether Mozart is better than Beethoven, it's a subjective question. People can ask that question, have debate. It's not a scientific question. We can't test Mozart or Beethoven and find something like that. Okay, so the model that we have in the back of our mind then, that we have statements, and the statements must be true or false, and then we have tests. And the test may succeed in finite time, can fail in finite time, or they might be undefined because they don't terminate in finite time, or because they don't give us a conclusive evidence. And this means that we have a two-logic system for the statements and a three-logic system for the tests. And it's this relationship between the two that actually gives us a lot of the mathematical structure. And we're going to say that a statement is verifiable if and only if, whenever the statement is true, the test is going to succeed in finite time and vice versa. So the test is always guaranteed to terminate if the statement is true. So, for example, something like the mass of the photon is exactly zero, right? Well, that's not going to be a verifiable statement, because we're never going to be able to make an experiment that in finite time is going to measure the mass of the photon with infinite precision and tell us that it's exactly zero. That's not going to happen. But the mass of the photon is less than 10 to the minus 13 electron volt. That's something that we can do. It finishes in finite time, and if the statement is true, we are going to get our answer, and it is actually true. Okay, so these are the type of statements that we can verify. Things, for example, that have a bound are things that we can verify in finite time. Things that are statements of infinite precision, we're not going to be able to verify in finite time. This seems silly, but the point is that just with this thing, you recover topologies and sigma algebra that if you're a physicist, you probably don't know what they are, but they are the most foundational structure that we have in mathematics. And this structure that physicists might not know what it is, and for mathematicians it's a very abstract structure, it's actually a very practical structure. And it tells us, it keeps track of what is experimentally verifiable or not. And the map works like this. The points of a topological space represents the physically well-defined possible cases. What can possibly happen? So all the possible values of the mass of the electrons, those are possible things. Those are the points of the state. The open sets represent, that are the sets in the topology, represent statements that are verifiable experimentally, where we can succeed in finite time if the statement is true. And if you have a real line, the open intervals are open sets. So these open sets correspond to the verifiable statement, the mass of the electron is within this bound. Conversely, a closed set is something that is falsifiable. So for example, the singleton 510 corresponds to the mass of the electron is exactly 510 kiloelectron volt. It's not verifiable, but it can be falsifiable, because as long as our uncertainty is small enough to exclude that value, then we know that that value is not true. And Borel sets instead represent statements that are associated with tests regardless of termination. So we can still think of how much we can say about these things experimentally, even though we might not be able to say anything. So for example, the set of all the rationals is a Borel set, so it's a theoretical statement, would correspond to the mass of the electron in kilo electron volt is a rational number. Now, mathematically, the interior, therefore the part that terminates in infinite time, is empty. So the test is never going to terminate successfully. The exterior of the set is also the empty set, and therefore the test is never going to terminate unsuccessfully. The test is never going to terminate, which means this statement is completely undecidable experimentally, which makes sense because the only way to know whether the mass of the electron is a rational number or not is to have an infinite precision measurement, which we cannot do. So there is a very, very perfect map between mathematics and physics that also tell us why functions in physics have to be well behaved. It's not just because in physics we're lazy and want well-behaved functions. No, because the well-behaved functions, which are going to be the topologically continuous functions, are the one that preserve experimental verifiability. So there is meaning as to why you can have analytical discontinuity when you go through different phases, because those if you look at how we can verify things, those are going to be topological isolated research. Okay, so we can again go through all the details of this. Probably most people that do physics don't know what this is, but the point is that you can make a map that is very, very tight, and that's basically what gave me confidence that this program of physical mathematics can actually be done and can be done at the higher level, because at this lower level things make a lot of sense. So for example, the sigma algebra, which corresponds with this Borel set, this theoretical statement stated associated with the test. The sigma algebra is exactly when we want to define probability, we need to use a sigma algebra to define the probability. You can't just use all the sets, you can only use the Borel sets. And physically that makes sense because those are the things we are associated with tests, and so the probability can only be meaningful if we are talking about statements that are associated with tests. And if you're a mathematician, you know that restricting yourself to Borel set, that's how you avoid the problems of the Banach-Tarski paradox and all other things. And there is physical motivation as to why those things work like that in mathematics, because the physics tells you that they have to be like that. Now, another thing that we're trying to build right now, it's this theory of states and processes, something that is general and works for everything, so that we can talk about states and processes in general, regardless of whether we're doing quantum mechanics or classical mechanics or other theories, and then we can have a common language on which then we can do reverse physics a lot better, because all the structure looks similar to each other. And again, we start with another principle, and it's the principle of scientific reproducibility, that the scientific laws describe relationships that can always be experimentally reproduced. This means that the scientific laws are relationships between ensembles. The physical laws are not what happened or what's going to happen at a specific time in the future, or what happened in the past in this case. No, it's things that we can reproduce. Every time we prepare something, we are going to measure something else. And so the relationship then, it's not about all the single instances, but it's about the preparation and the measurement as a collection of infinite instances of preparation and infinite instances of measurement. So the idea of ensemble is the core thing that all physical theory must at least give us, in the same way that we must at least have some notion of verifiable statement. And again, these concepts are general enough, vague enough, that we can construct a general theory, but we can characterize them mathematically precisely, such that this general theory can actually be mathematically precise. So, for example, we're going to have a preparation, and we're going to have an ensemble that comes out of the preparation, and this is the initial ensemble. Then we can attach a process, and this process will map an ensemble to another ensemble, but the process and the preparation together can be seen as another preparation procedure. And then we can have a measurement, and the measurement is going to take the ensemble that is coming in, and it's going to give us an ensemble of statistical data. And again, if we take it all together, we can imagine this as sort of a whole preparation of the statistical data. So when you're running your experiments, it's like you prepare everything, you click and you'll make it go, and then you gather the data and look and analyze the statistical data that you get on the side. So studying ensembles and relationship between ensembles and map between ensemble spaces, this is what we must have at least in any physical theory. And it turns out that that's a good way to think about physical theory in general, because a lot of structure comes out for free. So we have a preparation. This is the ensemble that comes out of the preparation. Not all elements are going to be equal to each other. There's going to be some variability of the elements within the ensemble. And the entropy is exactly what quantifies that variability. So for any ensemble, we are going to have an entropy associated with the ensemble that tells us what is the variability. Now, this other ensemble is going to have some other elements. And you see, these are mostly the same. These, instead, there is more variability because there is more difference between in the set, the distribution is more spread out. You can also see that these two ensembles always spits out something different. They're mutually exclusive in the sense that if you only see one instance, you're going to be able to say, oh, you prepared from P1 or prepared for P2. And so if you're trying to send information across, right, and if you are trying to transmit one bit of information, you will want to have mutually exclusive ensembles such that every time you get an instance, you're going to be able to say, oh, you prepare one or you prepare the other. And what happens is that this mutually exclusive ensemble maps to the notion of orthogonality, both in classical mechanics and quantum mechanics. And the trick is that we can characterize this orthogonality by how much the entropy increases during mixture. So we have these two preparations, we can create a mixture such that we can take, for example, 50% of this and 50% of this, and we're going to have certainly the variability is not going to go down when we're making a mixture, but it's going to go up. And the maximal increase is going to be when the two ensembles are orthogonal, when they're mutually exclusive. And what we can show, without even knowing whether we have a classical system or a quantum system, is that this increase in entropy is really the Shannon entropy. And we recover that formula and we show that's the only possible formula with very, very little assumption. So the idea is to really to create a general theory that works with only these idea that I have ensembles, that I can mix them, that I have an entropy, and start understanding foundational concept with just this idea. One of the things that we can, for example, distinguish is the notion of an identically prepared ensemble, an ensemble where all the elements are the same, from a pure ensemble. And a pure ensemble is one where no process can reduce the variability of the ensemble. That is, there's ensemble A2, right? There is no A such that E2 can be seen as the mixture of A and B for something else, with A with something else for some probability. So this is the best that we can do. And in classical theories, all pure ensembles are identically prepared. So in a classical theory, everything is of this type. And therefore, there is no real distinction between ensemble, like the whole infinite collection, and the instance, because if I know what the instance is, I have completely characterized the ensemble and vice versa. In non-classical theory, the things that is different, the things that is confusing, is that there are no identically prepared ensembles. So we can lower the entropy and get to the zero, but the zero entropy does not correspond to identically prepared ensemble. It corresponds to the variability of the noise, or the interaction with the environment that you can't get out of. And so what happens is that if these two things are different now, when we're characterizing an instance, it's a completely different thing than characterizing the whole ensemble. The whole ensemble always have some variability, and that corresponds to the uncertainty principle and the variability that you have in quantum mechanics. And we cannot just think about the instances, because now the instances are things that are fleeting and are not things that we can reproduce reliably. So since the laws of physics are about things that we can reproduce reliably, we need to have a reliable preparation, and the statements are going to be about the reliable preparation, which is going to have a minimum variability that you can that you can't get out. And once you understand things like this, a lot of things in quantum mechanics make sense. So for example, if you go back to the previous slide, you're going to always have some variability for the pure state, and the inner product is going to tell you how much overlap there is in that variability. If they're mutually exclusive, if they're orthogonal, there is no overlap in that variability. If they're the same things, there is totally overlap in that variability. And if you are in between, well, then there is some variability, and the inner product is actually going to be able to quantify that variability. So that's why the inner product, the geometry, is actually entropy in disguise. And so the idea is again to find a minimal set of requirements from the ensemble space. We saw before the experimental verifiability gives us a topology, the ability to mix things gives us a convex structure, and the fact that we have ensemble variability, this is going to give us an entropy and therefore the geometric structure. And I'm sure that we're going to need something else for the Poisson structure, the commutator. I don't know exactly how to generalize that, but that's why this is a project that I want to sort of advertise before having results, because I want actually people to come and help me out. So some of the general results that you can get from this structure, as we saw before, the entropy increase is uniquely determined and is the Shannon entropy. We can show that ensembles must embed in a vector space, and if we're able to show it continuously, we kind of are able maybe to show it for finite dimension. We can't show it infinite dimensional yet, but if we were able to do that, then we most likely would be able to connect to calculus of variation and all of that math over there. We're able to show that if we look at how much of the entropy increases during mixture, this is going to be able to give you a pseudo distance that actually recovers the Jensen-Shannon divergence in both classical mechanics and quantum mechanics. And the Hessian of the entropy, the minus the answers of the entropy, recovers the Fisher-Rao metric in information geometry for both classical mechanics and quantum mechanics. So the idea is that maybe we can have a more general structure in which we can do both. And then the other thing that I want to talk a little bit about is non-additive generalization of probability and non-additive generalization of the count of states. And this is one of those interesting things that are sort of clear after the fact, right? So there is a problem if we want to count states in the continuum. Ideally, what we like to have that every state is a single case. So if we do the measure over a single state, we will get one. That if we have a finite continuous range, that would carry finite information. So we have a finite range for some variable, then that the measure of how many states we have, it's finite. And we would also want the count to be additive over disjoint sets. If we have two different sets of states that are disjoint, then of course the number of states have to sum. And the problem is that all these three things are incompatible in the continuum, because if we have a sort of a finite range, from 0 to 1 on the continuum, there are infinitely many points, and if each point counts 1, then if we add additivity, we're going to get infinity. So these are incompatible, and we have to pick two. Now, if we discard the first one, we basically say we have finite continuous range is finite and the count is additive, then we get the Lebesgue measure, what we have typically on the continuum that we put on real numbers and what we put on Rn. If we discard the second one, then we have the counting measure, and that's what we usually typically in classical discrete spaces. Now, what happens in quantum mechanics is that you can generalize this count of states by looking at the exponential of the entropy. So instead of defining the entropy as the logarithm of the count of states, we're going to define the count of states at the exponential of the entropy. And if you do that, you are going to get a measure of count of states that satisfies the first one, but it's not additive. And this is how it works. If we have a pure state, well, a pure state is going to have entropy 0, so 2 to the 0 is 1, so every state counts as 1. So we satisfy the first one. If we have two orthogonal states, then the entropy, the maximum entropy that we can get by mixing those two things is going to be the center. So we can, with those two states, we can reach 1 bit of entropy. So 2 to the 1 is 2. So now this set corresponds to 2 states. But if we take two states, let's say A and C, that are not orthogonal, we are going to get a count of states that is less than 2, because we are not going to be able to increase the entropy by 1. We are going to entropy increase by much less. And so it's going to be less than 2, which is the sum of the measure of A and C. So the idea is that the measure is additive only on orthogonal states, because orthogonal states define cases that are mutually exclusive, that are different and all else being equal. I've prepared spin up or spin down. I didn't change the magnetization. The magnetization is always vertical. I just changed the energy level. So those two things are two different cases of the same scenarios. If you have non-orthogonal states instead, these are different states but are defining different contexts. So if I have a spin up or spin right, well, I had to rotate some magnetic field to prepare one or the other. So these things are not really mutually exclusive in the same way. Therefore, there are two different states, but they're not completely different. There is some overlap, and that's why the measure is not active. So in the same way that we saw that quantum mechanics puts a lower bound on the entropy, well, we can also think of quantum mechanics putting a lower bound on the count of states, 1, the entropy of 0 means the count of states 1, on a continuous degree of freedom. And why is this interesting? Because the conjecture that I have, and this is where, again, we go back full circle, these ideas might actually help us to understand what we need for quantum gravity, is that the problem that quantum gravity has to solve, maybe other problems, it has to solve other problems, and one problem that it has to solve, it has to put a lower bound on the count of degrees of freedom, not states of degrees of freedom. Because ideally, we are going to have that the number of configuration is the number of degrees of freedom times the number of configuration per degree of freedom. So if we're putting a lower bound on this, we need to put a lower bound on this as well. Otherwise, we can go and get as many low configuration as we want. And so we're going to have the same problem, that we will want that every point in space and every point in phase in a field theory is going to be a degree of freedom, or that's a set of degrees of freedom depending on how many fields you have. Every point you would like to have corresponding to 1 degree of freedom. A finite volume should carry finitely many degrees of freedom, and you want the counting to be additive in this joint region. So you will want essentially the spatial volumes, what we have right now, is a proxy to saying how many degrees of freedom that we have. But again, we have the same problem. We have to pick 2. And most likely we have to get rid of this additive idea. Like the count of degrees of freedom, if the 2 points are distant, they're going to be completely independent degrees of freedom, and therefore they count as 2 generally different degrees of freedom. But if the points are close enough, the value of the fields cannot be completely independent from each other, so the degrees of freedom are not independent, and so to compute correctly the entropy and so on, we need a count of degrees of freedom that sort of takes that into account. And so the issue is, from my perspective, that we saw that in quantum mechanics, putting a lower bound on the state count required a severe revisitation of the particle state space, to the point that we really didn't even understand what we were doing, right? And so, you go from classical manifold to this Hilbert space and so on. So the math is very different. There is a significant leap. And what I worry about is that if we want to put this lower bound on the count of degree of freedom, maybe we'll require a severe revisitation of the mathematics that we use. So maybe we don't even have the correct math to actually create a theory of quantum gravity. But of course, this is not my specialty. And as I said, this is not my main problem. My idea is let's go and dot all the I's, cross all the T's on the theories that we have before trying to go and create new ones. And maybe once we've done that, creating the new ones is going to be a lot easier. Again, so we now go back at the picture that we had before. For us, the foundations of physics is really creating this model of all the physical models. We're going to have some physical principle requirements that give us a general mathematical framework, and then specific assumptions that recover the different instances of the different theories. And this must be a considered effort between physics, math, information theory, philosophy. A lot of things have to come together. I can't know everything. I try to know enough such that I can talk to logicians, topologists, differential geometers, information theorists on the quantum side. I need to be able to talk to all about it, but unfortunately we don't even have a common language, and this makes this type of project significantly different. So this is why I'm trying to running this as an open project. Our main output is our open access book that it's on GitHub, and people can go and submit patches to fix all my typos and the problems that might be there. But of course, you should probably coordinate with me than just sending a pull request. I have a YouTube channel dedicated to publicize the result, this YouTube channel. I have another channel dedicated to the research where we have the live streams discussion. Right now we are hosting a reading group, but if people want to discuss detailed things, I'd like to have all those discussions on YouTube live, but unfortunately a lot of academics are timid and they don't like doing that, so unfortunately I can't do it as much as I want. Not everybody's crazy like me, but anyway, so whatever people can do to help me setting up this whole project is appreciated. So I'm always looking for experts, I'm always looking for collaboration, people that can even help me on social media or other ways, anybody who is sympathetic, because as I said, this is a humongous enterprise, but I don't think we're actually going to go much further in the foundations of physics without something like this going on. So wrapping it up, we have a different approach to the foundation physics. We're not interested in interpretation on theories of everything, but in physically meaningful starting point from which we can rederive the laws and the mathematical frameworks they need. We have an approach called reverse physics that starts from the known physical laws to find a physical principle. Classical mechanics is essentially completed in the sense that we have all the major things. There are always little details that can be improved. If people want to help me improve things, that's fine, but I need to work on the pieces that are missing, such that thermodynamics, we have very good ideas, and also quantum mechanics, I have a very good idea. I'm actually starting to work on the reverse physics of quantum mechanics. And field theory is the things that I still don't know. I have a student right now that is contacting me that maybe is going to help me do some stuff, but you know, I really need help there. This is not something that I have under control. I don't know exactly what needs to be done. On the physical mathematics side, then we want to rederive all the mathematical structure from scratch. So we already have a very, very precise way to derive topology and sigma algebra from experimental verifiability, from this constraint. We have a good progress on a generic theory states. And again, if there are people who are mathematicians and they want to help me review the proofs and maybe try to help me prove some conjectures, I'll be glad as well. You know, you can leave a comment below or you can contact me. I'm very easy to find. The goal is ambition. As I said, it requires a wide collaboration, and I don't know how to pull it off because I have no example, but I do what I can. And this is why I have videos like this on YouTube in case people randomly see things and want to help. So that's it. To learn more, you can go to our project website, to the channels. You can look at GitHub. If you want to know more, you can also subscribe to the other YouTube channels to see more of the details of the research. If you want to donate, there are links in the description. That is also very much appreciated because there aren't really many sources of funding for this type of interdisciplinary work. There basically aren't. There are only a few private foundations that might give us something. So again, the funding aspect is also something that needs to be understood. But thank you again for your attention. This video was probably longer than I expected it to be. And thank you again and see you next time.